Okay, guys, welcome to our week 11 lecture of the superstructure component of the structures 2 course. And today will be our last lecture topic, but we still have next week lecture. It will be revision, and I will discuss with you the exam arrangement. And in this week, we will have some objectives. We will learn some information about the buckling theory and the design of columns and are the loads on the columns and how to design a column. This part will be also needed or very important in your part 2 of the project. And I hope you have go through the example of beam I have shared with you. So this example will help you to design the beam of the report or the project, beam B2 as well. Do you have any question about the project or anything before we start? I will soon release the video for the space gas. I just was busy a little bit the last 2 days, so I will try to post it as soon as possible. So don't worry about space gas, and also I will clarify some details of the assessment very soon. Okay. So I received a question from Alex. Calculate the axial force for the critical load combination for column. Are you going to show as this today? Yes, and also if you look to this example here, so this example I will go through it in the during the classes tomorrow. So this example is exactly what you need to do for the project, similar type of column. So this will help you to understand more the requirement. Today I will go through the concepts, but not an example. Okay. So for Alex questions, you can have a look on the solved example until I discuss it tomorrow. Okay, guys. Any other question about beam or column? Okay, so let's start our lecture today. When is this guys video going to be ready? Tomorrow, inshallah, Yog. I was just busy to prepare the slide because the old slide was not showing the examples I shared with you. So that's why I have to create new slides for you the last few days. So that's why I was busy I don't have time enough to finalize the video as well. So the video will be ready by tomorrow, Sean. Okay. So let's start our last topic about the columns. We have already designed the beam last week in the lecture and in the class. So today we will have the topic about the column design and how to design a column. So for column design, the columns are usually designed for two forces or two type of forces, axial loads or axial forces, and or with moment. So the column can be designed for normal force only, just number one, or normal force and bending moment. So the first part will be designing of column under axial load only or axial force only, which is N. If you remember for rafters or beams, the beams we have calculated the bending moment and shear. So for beams, bending moment and shear. For rafter, we have column and if you have for the column, sorry, we have axial load and moment. So this is an summary of that. So for structure members or structure elements, like beams and columns, we have some actions or straining actions that we design each member for. So the first thing is beams. Beams are designed for bending moment and shear. So bending moment and shear force. Okay. And for columns, they can be designed under actions, which is axial load or axial load and bending moment. So this is the axial load and those are the moment. Here in this case, only axial load. Okay. Another element, we are not dealing with this course in this course, but it is the truss element. The truss element is quite similar to columns, can be considered as column because the truss element or the truss members are designed under axial loads, which is tension or compression. So if you remember in structure one course, you have the test, the like the the truss testing, and all the member in the truss are subjected to tension and compression forces. So our focus today will be about columns. So we have two type of design for columns. Columns under axial load only, like this one, and columns under axial load and bending moment like this one. Okay, now why the design of column is too important for us? Because as you can see, the column failure will cause severe consequences if it is collapse. So as you can see here in this building is a reinforced concrete building or reinforced concrete structure. And as you can see in this circle here, we have here column failure or column collapse. The column collapse cannot be like rehabilitation or can't be fixed. So the column failure cannot be fixed. So this means that this building totally collapse. If a column collapse or like two or three column collapse, this means totally failure or total collapse of the building. So the columns are the most important structure members because the collapse of a column is a disaster and will cause failure of the entire building. But for a beam failure, like for example this beam or any other beam, the beam failure can be fixed. So you can strengthen the beam or you can replace the beam with a steel beam and so on. But the problem is if the column fail, so there is no other option. So the total collapse will occur. One of the problem we face with the columns is the column buckling or the buckling of the columns. So the buckling is an issue combined with compression. So any member under compression may be subjected to buckling. So when we are designing the column under axial force, we have two cases. Member or column under tension, like this one. So the force is pulling the member, or member under compression, like this one. So our buckling problem will be within this one, the member under compression. So if we apply compressive force, the column can buckle, but the tension force, no option of buckling or no fear from buckling. So the buckling occurs when a force presses on a cylinder member, causing failure. When we apply large load on the column, this can cause the buckling, and a cylinder column will fail due to this buckling. So when you have a column or a cylinder member like a column, when you push it like this from top and bottom, what happened to this column? This column will buckle. Or let's do it in the other side. So the column will buckle. So this movement or this displacement is called buckling. And due to this buckling, the column is considered as failure. So we need to avoid or make sure that the column will not buckle during our design. One of the example of column buckling failure under compression load is this example. Again, this is an RC column, but due to buckling, as you can see, the steel bars inside has buckled like this. So when the steel bar is buckled, it pushes the concrete or the outer cover of concrete and causing failure of the column. So this buckling problem, again, associated with the compression and need to be avoided. Another possibility or one of the major causes for buckling or column buckling is the long column. So as you can see in some cases like entrances of hotels or shopping center and so on, we sometimes need to have long columns. These long columns are also thin. You can see the diameter is too small, so we have thin column. So due to the long column and thin thickness or thin size, this column will buckle. Okay, so this movement is more noticeable in long column. So buckling is more noticeable in longer columns. So buckling is a critical issue and clearly affects the long or the cylinder column. Cylinder column, we like call the long column also cylinder column. So this means it is a very long or very tall member with very small or thin width or thickness. So we have a long column with thin thickness. So this is considered a cylinder member. And here also another example of buckling failure of a column. As you can see, this column is big column. It is a column of a bridge or abutment of a bridge. But as you can see, this column still have weak dimension. So as you can see here, this is a short dimension and this is the long dimension. So the column has buckle around the short direction. So if this our axis, so the column has buckle around this axis. So if we draw it like that, so if this is the column, so we have two axes, one of them this one of them in the other direction. So this axis is called the weak axis. So this axis where the column will start buckling about or around. Okay, so the column will try to buckle in this direction or this direction. So usually or mostly buckling occur around the weak axis of the cross section because it will be hard to buckle about the strong axis. The strong axis in this case is this axis. So this we call it strong or major axis. So the buckling mostly happen about the weak axis, or we also can call it minor axis. We will see a video to explain the major axis and minor axis now, but let's have another information here. So now we know that columns are when they are under compression. So we have a problem of what? Buckling failure. So this is the first mode of failure that can happen to a column under compression. The column under tension, we don't have buckling issue, but we have another issue which we will see now. So other modes of failure, so this is what we call failure modes. Why we are worried about the failure mode? Because the design principles are, or design procedure are based on failure. They based their design series based on the failure mode. So let's consider we have a stocky column, very short column, like the one here in this photo, subject to an increasing axial load. This column will eventually fail due to compression when the material compressive strength exceeds when the compression or the compressive strength exceeds the material compressive strength. So this means in stocky columns, we will not have buckling. Buckling is too hard to happen in the stocky columns. So actually what will happen is due to the column is too short, it will be too hard to buckle. So it will fail due to what we call yielding. Yielding mean the stress in the member is more than sigma yield of the material. Sigma yield can be named as, we can put it here, sigma yield is the yield strength or the strength maximum strength of the material. So this case number one or failure mode one. So failure mode one will happen in stocky columns when the column is impossible to buckle as it is too short, so that the column will fail due to what we call yielding. The second option is if we consider a longer or cylinder column subjected to an increasing axial load, so the column will start to bend. This bending means buckling about the weaker axis. So again here, as you can see here, if this our column, but this column is cylinder. So when you apply the load B, this column will bend in one of the direction like this. This bending we call as buckling and deflect sideways when the load reach a certain value. This phenomenon called buckling. So our second failure mode or failure mode 2 is what? Buckling failure. So this is the two option we may have in columns. So we have mode 1, yielding. We have mode 2, buckling. So if I ask you a quick question to see if you understand this. So for compression, we can have buckling or yielding. For tension, how many mode of failure we can have? Do you know? As no buckling could happen or could occur for tension member. So the only mode of failure for tension is yielding. So for buckling, sorry, for compression member, we have two modes of failure. For tension failure, we have only one mode of failure. Okay. So this is buckling, and let's have a quick look on this column. So I will show you this video, and you can see this later. Sorry guys, I have to get this link out.
This video shows a pin-ended column of low slenderness being tested in compression. This type of specimen is commonly referred to as a stocky column. The specimen is a rectangular hollow section made of structural steel. The length has been chosen such that the failure is dominated by the material strength. The loading diagram shows a purely axial compressive force evenly applied to both ends of the specimen. The testing rig is now starting to apply a compressive force to the specimen. We can see the top end displacing and the column begins to deflect sideways as a result of the material damage, which can be seen at midspan on the concave side. Once this occurs, the column begins to lose its load carrying capacity. This particular phenomenon is not in the elastic but in the plastic range. Therefore, the failure is governed by the material rather than the geometry of the specimen. Turning the specimen to the side, you can see that the deformation has localized to the midspan of the specimen in a plastic hinge. The graph initially shows a linear relationship between force and displacement. In this range, no sideways displacement has taken place. However, once failure takes hold, the slope begins to reduce rapidly, and the point at which the curve becomes flat marks the failure load.
Okay, guys, this was a video of the column buckling testing or compression testing, which lead to failure of the column due to buckling. Okay, the summary for what we have done already in the columns. First, thing is columns failure will cause serious problem in structures. There are two column failure modes. One of them is the buckling failure. The other one is the yielding or material failure. The third point is buckling is a problem of compressive member with insufficient lateral stiffness. So again, the buckling is an issue associated with compression member only. Okay. Now, when we are designing a column, we need to consider the column buckling in our design. So that we need to know how the buckling looks like in other member on the members. So in this table, this is what we call the effective length of compression member. So as you know, any column, so if we have a column, so the column can have support, should have support at the top and at the bottom. So we have one case, the column is bent at the top, bent at the bottom. So each column has two ends, top end and bottom end. Okay, these two ends will impact the buckling of the column. So when you are designing a column for buckling, or when you are designing a column, you should know what are the type of supporters this column have. So one of the cases, or the first case we have now, is bend column. If the column is bent at the top, bent at the bottom, so this column will buckle in shape like this. Okay, so we have two lenses now. The green one is the original length of the column, and the black one, in this case, is the buckling length of the column, or we call it LE. So LE, we call it effective buckling length of the column. So in the first case, bin column, we have L effective equal to L. Okay. So this because the column started to buckle from the first point at the top and start to buckle at the bottom end of the column. Another option or another type of support we may have is fixed column. If the column fixed at the top and fixed at the bottom, so in this case, we have fixed support and fixed support at the bottom. So in this case, the column will not start buckling from the top point because of the fixation. So it will start a little bit later. So this is the buckling shape. So the buckling shape in this case, because it doesn't start from the top, the buckling length, they found it as L effective. This is our L effective, and this is our L. So as you can see, L cannot be taken as equal to LE because as you can see, the buckling start a little bit later. So here in this case, the standard take L effective as 0.5 of L. So in the first case, L effective equal to L. Second case, L effective to 0.5 of L. The third case is the mixed case if we have fixed at the top or at the bottom and hinge on the other side or bend on the other side. So in this case, the column here will start buckling a little bit later, not at the point of support. Here it will start from the bottom point directly. So now here is our L effective. So if this is our L, L effective is a little bit less than L, and it is more than half L here. So it is something between this value and this value. So they take the average as L effective in this case equal to 0.7 of L. Okay, so the standard give us three cases or three, like we call it ideal cases for supports for the column or for bin supports for the column. The first one is bin. Second one is fixed. The third one is bin fixed. This information of LE will affect us when we are designing the column. So this means, just for your information in the next part, that when the column is bin, the critical buckling height or the column will be more susceptible to buckling because we have the whole L is under buckling. And the best one for buckling is fixed because only half of the column will be subjected to buckling. And the bin fixed case will be in between, something in between the two cases. So now if we return to this table is a table given in the Australian Standard 4100 version 2020. This is the steel structure design standard in Australia. So you can also have a look on this one so that when you are designing a rafter from steel or a column from steel, you will have idea what is the procedure for design. So now for our columns, this is the members with idealized end restraint. So actually the bin and fixed support I show you earlier, these are not the actual supports or actual restraint. These are like theoretical or idealized restraint because in real life it will not be that ideal. But let's have a look on the ideal restraint case. So the first step we have braced members and sway member. Let's focus on the braced member first. For braced member, as I show you earlier, if we have a column bin, so how much is the factor KE? KE is 1. What this mean? This means that L effective has a relation with L, which is KE. So KE is the factor I show you earlier. It is 1 for bin, 0.5 for fixed, and 0.7 for bin fixed. So in this case, LE equal to L. In this case, they take it 0.7 here. Okay, so I will just update this one because actually we have two cases for this one. So this one will be taken 0.5 L for theoretical calculation, but the standard we will go like follow the standard here. So I will make it 0.7. This only for standard. So this 1.7 because the standard sometimes takes factor of safeties for design, so they make it a little bit higher. So this one we will make it 0.58, 0.85, sorry. Okay, so just to follow the table, but there is another table in the standard. They have another factor below this one, which is 0.5 and 0.7 and 1. So I just don't want to confuse you more. So if we have bin similar to here, bin at the top, bin at the bottom, so L effective equal to L. If we have fixed at the top, fixed at the bottom, so it is 0.7. if we have pin or fixed at the top and the opposite in the other direction, so it is 0.85. Okay, so this is for member in braced frame. And for sway member means if we don't have bracing. So we will see this later in the next slide, but the factors are a little bit different and also the supports are different. So for sway member, as you can see, the member is fixed at the bottom, and if it's fixed at the bottom, it is rotation fixed and translation free at the top, or rotation free, translation free at the top. Okay, so for sway member, I will just take these three cases. So we have fixed at the bottom and rotation fixed and translation free at the top. Here we have the factor Ke equal to 1.2. So this 1.2 L. The second one, if it is fixed at the bottom, free at the top, so we have 2.2. If it is hinge or pin at the bottom and rotation fixed, translation free at the top, this is 2.2. Okay, so let's have a look on the braced and non-braced or unbraced meaning. So for column buckling, we need to understand what is the difference between braced member and on or sway members. So for braced member or braced column, this means that our column in a frame or in a shed, the column is prevented from sway using bracing, for example. So if we have bracing or if we have another like a member somewhere here to prevent the horizontal movement. So in the braced column, this means the column are prevented from sway or side movement. So if the column is prevented from side movement, so we call it braced member. So the column in this case is braced column. The other option is if the frame without any bracing in this direction, or we don't have any member that prevent the side movement. So if we have any force applied to here, what happened to this member? This member will slightly move horizontally. So we call this movement as delta or sway. That's why we call this frame or this column as unbraced column, or another option or another way we call it sway column. So sway column means that the column are allowed to move horizontally because no support prevent its movement or side movement. So now for our design, the effective length of the compression member or the columns will be based on two things. We need to know first if the column is braced or unbraced. Then we need to know what is the ends of the column. So to know LE of the column equal to KE times L To know KE or to know LE, we need to know two things. The column is braced or not. Number two is the two end restraint. Okay, so based on the column braced or not, we go to this side or this side. Based on the ends, so we need to know if it is bin or fixed or fixed bin, so that we can know what are the factor KE. Okay, let's see this table, this video, sorry.
Here is a teaching tool to demonstrate the different buckled shapes for your different end conditions that you can have at the top and bottom to support your column. So there's 4 different setups, and each setup has a thin piece of metal. Here is a teaching tool to demonstrate the different buckled shapes for your different end conditions that you can have at the top and bottom to support your column. So there's 4 different setups, and each setup has a thin piece of metal that acts as your column, and then the way that they are supported at top and bottom are a little bit different. So we can apply load to the top to perform this buckled shape. So first, for a fixed, and to get this fixed condition, you notice there's a slot at top and bottom to help prevent the rotation of that support. And if I push down slightly, we should see our effective length factor, K, the distance between our inflection points or points of zero bending moment, should be about half that total length of the column. So fixed. Then on to pin at the top, fixed on the bottom. If we apply a load here, we should see about 70% of that length between our points of zero bending moment. And then on to our classic case, our pin, we should see, about lost that one. Between our effective length factor should be the distance between the pins, which is L, so K equals 1. And then the last one, our pin free condition, this is backwards of what we have in our notes. The free end down here is free to slide, and this hasn't been greased in a while, so I need to cheat to start this one. But if we apply a little bit of a buckling load, we should see, that's not very good, we gotta go further. We should see our effective length factor of 2, the distance between inflection points. Once we take this shape and invert it on top, we would get a total effective length of 2 times L.
Okay guys, thank you. So this video to show the different end condition and the effect of the end condition on the buckling shape. Another video here will show us the difference between braced and unbraced frame. So let's have a look on this one as well. So as you can see here, the braced column, sorry, the unbraced column or the sway column, unbraced frame on the left side, and here the braced frame. as you can see, the unbraced frame was almost nearly to fail because of the applied like vibration load, or this simulates the earthquake loads, so that the buckling is more, or causing more problem in the sway members, because the sway member already under lateral movement or horizontal movement, so that it is a little bit more critical. That's why the factor KE is higher in the sway member compared to the braced member. Okay, now let's look on the two type of buckling we have for columns. So the column buckling, we have buckling in plane and buckling out of plane. So in plane means in the plane of the element or the frame. Out of plane means out of the frame, out of the plane of the frame. So for example here, if we have, this is our column, long column. So we have load applied on the column. So if this is the plane of the column, okay? So if the column buckle in this direction, or this direction, so this movement is in plane. So it is in the plane of the frame. But if we have another movement in this direction, so this means that the buckling happen out of plane. So this is out of plane buckling. So we actually have two direction of the buckling. One of them, as you can see here, if this is the plane, so this buckling happen within the plane or in plane. And if this is the plane, so this one happen out of plane. So when we study or when we investigate the column buckling in our design, we should check two buckling types. Buckling in plane, and this is more important to us, and out of plane. So the next slide will show us better understanding of buckling in plane and buckling out of plane. Okay, so if this our column, this is the original column, and it buckle in this direction. So this is in plane buckling. Okay, and this is buckling out of plane. So buckling in plane, we will have buckling length or L effective. So L effective in buckling in plane, we call it buckling length in plane. or we can give it L, the symbol LBX. And we have another buckling here in this case, which is this buckling out of plane. We call it buckling lens out of plane, or we give it the name LBY. So LBX is the buckling lens in plane, LBY is the buckling lens out of plane. This will be according to the names of the axes of the column buckles around. So because usually buckling in plane, if this is our column, so this is how the column installed in the frame. So this is the plan of the column. So we have two axes, as you can see. This is x-axis. So buckling in plan means the column will buckle in this direction. This is what it means. So this means that the rotation is about or around x-axis. That's why we call it LBX. So the in-plane buckling is LBX because it is happening in plane, or the buckling in plane happen around x-axis. For the same column, to buckle out of plane, or the meaning of buckling out of plane, if this our column and this is our frame, our plane, so we have this is y-axis, right? So y-axis, the column will buckle. In this case, the column will buckle in this direction. So this means that the buckling out of plane will happen or will occur around y-axis. If it happen around y-axis, we call it LBY. So the reason for the names is because out of plane buckling happen around or occur around out of plane occur around y, and in plane occur around x axis. Okay. So here is the, if this our axis, so the buckling in this case happen around x-axis. So this moment or this movement is in plane buckling. The in-plane buckling, we call the length of the column that will be under buckling in this case, or L effective buckling, LBX. So LBX is the buckling or the effective, the in-plane effective buckling length. LBX in this case can be KE times L. So whatever L KE associated with the in-plane buckling. So this for the in-plane buckling. For the out-of-plane buckling, in this case, the buckling will happen or will occur around y-axis. So the buckling happen in this direction. So this we call what we call it out of plane buckling. So the out of plane buckling will occur around y-axis, sorry. So the buckling length out of plane in this case, for example, will be this case. This is our LBY, LBY. We will see now why, but because we have support in the middle, this support in the middle will make this LBY. So whatever LBY, it will be LBY equal to K effective in this case times L. And LBY, the definition is the out of plane effective or buckling length. Okay? Any question, guys? Okay, so all the previous explanation, starting from this slide here, this was the buckling lengths or the column buckling lengths for idealized end restraint. This is what we will be using in our calculation for part 2 of the project. Another method to find the effective length factor is using charts. So for members in frames, or in other words, if you want to get the accurate K value, you need to use this method. So this method, we will not be using it in our calculation, but I just like briefly go through it quickly so that you have also some knowledge about it. So how can we find the effective length using this method? So in this method, as you can see, we have two charts, two type of charts. So the charts on the right hand side and left hand side. So for the right hand side, we have braced member. So if you are calculating for a braced member, you need to come to the chart. If you are calculating for unbraced or sway member, you need to go to this chart. Okay, what is the relation in this chart? It is a relation between stiffness ratio at end 1, gamma 1, and stiffness ratio at end 2, gamma 2. So as we mentioned, any column has two ends. One of them is end number 1, one of them is end number 2. Doesn't matter which one is top, which one is bottom, because this curve or this graph is symmetric. So we need to find a value of gamma 1 and value of gamma 2. So if you know gamma 1 and gamma 2, for example, let's say gamma 1 is 2 and gamma 2 is 2. So you create a line like that and a line like that. So they intersect at this point. So this is our KE. So KE in this case, for example, 0.85. So to enter this charts, you need gamma 1 and gamma 2, and you need also to know if the column is braced or unbraced. Okay, this method is a little bit more complicated compared to the other one, because the other one you go directly to the chart to find, sorry, the table to find the value. But in this case, we need to get the value of gamma 2 and gamma 1. And we need to know if the frame is braced or unbraced. In a similar way, for unbraced member, you will need to find gamma 1 and gamma 2. So same procedure but different value. So again, if we have gamma 2 equal to 2, gamma 1 equal to 2 as well. So we will create a line here and a line like that. So in this case, for example, KE equal to 1.6. So KE in this case 1.6, for example, here in this case, for example, K equal to 0.85. So this is just an example to how to, if you found gamma 1 and gamma 2, you can easily go to the table, or sorry, the chart to find the value of KE. So now the problem will be how to find gamma 1 and gamma 2. So gamma 1 and gamma 2 is a stiffness ratio for rectangular frame. The gamma value of a compression member in a rectangular frame with regular loading and negligible axial force in the beam shall be calculated as follows. This is the statement from the table, the standard AS 4100 version 2022. So what we need to do to find gamma? So for gamma 1, for example, the top end, gamma 1. So we need to know the rafter properties at this point. So we need to know the rafter. And also we need to know what the column. So gamma 1 is a relation between the properties of rafter and column. So for gamma 1 or gamma for top end, gamma equal to sigma or summation, the inertia of the column divided by length of the column divided by summation B effective I over L for beam or for the rafter. So you need to know I and L for beam, I and L for column. And then you need to know BE as well, beta E. So the definition of the symbols are IC, the inertia of the column, second moment of area or inertia. LC is the column length or the length of the column. IB is the inertia of the beam. LB is the length of the beam. Beta E is a modification or modifying factor. So beta E from the standard is equal to 1 unless the far beam end is bent or fixed connection. So if we are studying this point here, so we need again the probabilities of this rafter and the probabilities of this column. So now if we know IB and LB, IC and LC, we still need to find beta E. Beta E equal to 1, so usually it is equal to 1 unless the other end of the beam, so this is the other end of the beam. Is bend or fixed connection. So this table 4.6.3.4 for beta E give us the value of beta E if the far end is not a normal connection or if it is bent or fixed. So if it is bent, so if the column is braced, beta E will be 1.5. If it is sway, beta E will be 0.5. If it is fixed, if it is a braced member, so 2. If it is sway member, 0.67. Okay, so based on the far end, you will find how much is beta E. This for what? All of this was for gamma top end. For gamma bottom end or gamma 2 is the relation or the connection between the column and the base. So gamma 2 can have two values. Gamma 2, we will take it 10 or gamma 2 equal to 1. So you can summarize this to two values. Gamma 2 will be 10 if we have the base is pin support or hinged support, similar to this one or this one. So if the connection between the column and the footing is hinge, so gamma 2 is 10. For rigid end or fixed support, we will take gamma 2 as 1, similar to this footing here. So this footing is bent because it's allow for rotation, so it is not a fixed. Here fixed because we have bolts, so no rotation allowed. So if we have fixed base like this one, or in structure view, this is a fixed base, gamma 2 equal to 1. So gamma 2 equal to 1 or gamma 2 equal to 10 based on the type of support or the relation between the column and the base or the foot. Okay, so after you know gamma 2 and gamma 1, go to the table to find KE. This one if the member is braced, this one if the member is unbraced. So gamma 1 again, gamma 2 to find K effective. Okay, so this method will give us an accurate value. So the only importance of this method that this method is like provide an accurate value of KE and LE. But in our calculation, again, we will use the first method, which is the values from the table. So again, we will be using this method to calculate the values for KE and LE. Okay, any other question, guys, before we proceed? Any question? Okay, thank you, Harrison. Okay, now let's proceed with another also information to enlarge your knowledge. So any column under load, not every load will cause it to buckle, but it will buckle at a certain limit. So if the load exceeds the critical load, so this means the buckling occurs. Okay, and if B less than buckling critical load or the critical buckling load, so buckling doesn't occur. So what is this value or what is this limit? This limit is called B critical, or in other words, Euler load. Euler loads, because the scientist who found or proved it is called Euler. So Euler load B critical is the critical buckling load equal to pi squared E I divided by L effective squared. So L here is L effective. So the critical buckling load is sometimes referred as Euler load. Or buckling load of the column. The critical buckling load or the load capacity of the member depends on the column dimension, which are the moment of inertia, the buckling length, and the Young's modulus of the material. So as you can see from the formula, the buckling depends on 3 parameters. The buckling load depends on 3 parameters. Number 1 is E, which is Young's modulus. So Young's modulus is the modulus of elasticity of the member. So it is the material probabilities. Number 2 is I. I is the inertia of the member or the dimension of the member. So inertia or dimensions. Number 3 is what? LE. What is LE? LE is the effective buckling length. So these are 3 parameters that control the buckling load. So the load carrying capacity or the critical buckling load it is calling the load carrying capacity because after this value the member is considered as failed of a column will increase as the moment of inertia of the cross section increase. So the buckling load increase if I increase because B critical is proportionally related to I. So if I increase, this means that B critical increase. So if you want to avoid buckling, what you need to do? So to avoid buckling, you need to increase the column section. Similar to the rafter. If the rafter is not safe due to deflection, so what you do? Increase the column section. Okay, so this is the formula. And the moment of inertia I is not tested. Have you heard about the inertia before? Have you calculated the inertia before? So the moment of inertia is one of the probabilities of the cross section. We have used I in our deflection calculation last week. So I for a steel member is given in what? In the table. So I for a steel member is given using the table. But here in this slide, this is the definition of I, so I will not go through this part. So this part is not uh, related to our calculation, so that I will skip this one. Can you give me a second, guys? Can we have like 5-minute rest, please? Just need to plug in the laptop. Okay, we will have a rest for 5 minutes and then meet again. Okay, guys, let's continue. So again, the moment of inertia is a topic that we will not focus on. If we need the inertia for our UB sections, or inertia, I for UB or UC. UB universal beams sections, or UC universal column section. We can get it from the tables provided. Okay, so we don't need to worry about how to calculate the moment of inertia. So a column, just to continue with the buckling analysis of column equation, a column will buckle about the principal axis of the cross section having the least moment of inertia. For example, a column having a rectangular cross section will buckle about the AA axis, not the BB axis. So this means that the column will buckle first around the weak axis or the minor axis. So this logic, so because it is weak, so weak axis or minor axis means less inertia. So the weak axis is the axis with less inertia. So here, if this axis BB and this is axis AA, so this column will buckle around AA. Okay, because AA is the weak axis to this cross section. BB is the strong axis. Similar to the video we have watched, the column will bend about the weak axis, not the strong axis. Okay, so in summary, for the buckling equation and design equation, if we have a column under the buckling critical load, or B less than B critical, or up to the critical load, so the maximum axial load the column can support when it is on the verge of buckling is the critical load. So if the load is subject to B less than or equal to B critical, so no buckling will occur. When the buckling will start, or when the buckling will occur, when B applied load more than the critical load. So if the load applied exceed the buckling load, the column will start buckling and the column will start failure. Okay, so it will keep buckling until it fails. So this is the original column, and it will keep buckling until it fails. So this is buckling failure of the column. So any increase in the load will cause the column to buckle more. So this column is considered failure. This column is no failure. So now when we are designing a column, so now we know about the buckling and we understand that these columns are designed due to N only. N means axial load. Okay, how we can design this column under axial load? The idea is the standard, to run a standard, we have two values. We need to make sure that the applied load or B actual be less than B critical. If it is less than B critical, so this means our design is safe. So this is our design principle. But because we also have some uncertainties about the critical load and we may have some like inequality control problems, so that they are using a capacity factor phi. This phi is a factor or a reduction factor. So we just assume that we will lose part of the capacity a little bit so that we are in the safe side. So this means that B should be less than phi BCR, or in other words, using the standard 4100. N asterisk, this is the applied axial load. Should be less than the member capacity. So can be written in a different form to make the member safe. N asterisk divided by phi NC should be less than or equal to 1. Okay. So this is just a summary or a brief summary of the design formula. And now how can we design? So similar to last week, I will just keep the charts. There is table as well, but I think it's better to focus on the charts. So we will use the charts only for design. Okay. Similar to the rafter in last week section or last week class. So let's have a look. This is a design chart. We will have two charts, or we will design 2 times. We will go to the chart 2 times. So to design the column, we have case 1. Case 1, you go to the chart using N asterisk and LBX. So we will check the column under two cases. The first case, we have the axial load, applied load, and LBX. What is LBX? Buckling or in-plane buckling length. So what we will do, we need to go to this table or this chart, sorry. This chart, just to be careful because this chart we have charts for beam and charts for column. For column, you need to use the universal column chart. So this is the first point. Second point is the chart a relation between effective length about x-axis and the axial capacity or axial compression. So this is the chart to use with N asterisk, or in the case of N asterisk and LBX. So for example, if we have N asterisk equal to, let's say, 1000, and LBX, let's say, 15 meters. So I will go to the table or the chart using these two values and try to find the reasonable section. So let's start with the horizontal axis, L effective. So L effective 15 meters. So this is our point, LBX equal to 15. And I will create a line, dashed line like that. Then we have on the horizontal axis, sorry, on the vertical axis, n asterisk 1000 kilonewton. So at 1000 here, this point n asterisk equal to 1000 kilonewton. Then I will create another horizontal line here. So these two lines intersect at this point. So which graph is, or which chart, or which plot is our plot? We are between this one and the bottom one. So we are taking the top one. So if we look to the top one, so this is our selected chart or selected section. So the design of this column is use a column 310 UC 96.8. So this is our design. So the first step or the first case, you need to check or find the suitable section for n asterisk with LBX. The second step or second case is what? What do you expect? The second case is to check, or case 2, we check n asterisk and LBY. So again, we need to use the correct chart. So again, universal column. So this is the first thing. Then on the bottom axis, oh sorry, on the horizontal axis, what you can see, L effective about Y axis. So you can't use Y axis for X axis. So just be careful when you are using these two charts. So one chart for Y, one chart for X. So this was similar to previous step. Now if we have same n asterisk was 1000 kilonewton, but here LBY may be a different value. Let's say it is 5 meter. So what we will do, go to the table, sorry, the chart, using 5 meter. Here is our point, LBY equal to 5 meter. Then we create a dashed line. And n asterisk 1000. So at 1000 on n here, 1000. So n asterisk equal to 1000. I will create a horizontal line. So these two lines intersect at this point here. So this means that this curve or this column is suitable for us. So if we look to this column, so 200 UC 59.2. So for LBX, we need 300 UC, and for LBY, we need 200 UC. So which column to use? So the final design is the biggest one. Use the one from this case. So we use 310 UC 96.8. So actually, this is the one we used in the previous step. So it is satisfying because it is above this curve. So this curve is okay. So our final design will be this one here. Okay, so it is similar to what we have done in the previous week for rafter, but we need to go to the charts using the value of n asterisk and lbx and lby. In the previous week, we go to the chart using m and l effective. Okay, so this case, or this is the design method for column. So actually, all the problem you will have, or all the calculation you will have, how to find n asterisk. This is what I will explain tomorrow in the tutorial example, and how to find LBX. How to find LBX? LBX will be found using the factor K effective from this table. So K effective will be 0.7 or 0.8 or 1 if we are braced. If we are sway member, 1.2, 2.2, or 2.2. Okay, so this column design, this is what we will be using in our project part 2. So the column C2 in your project will be a column only subjected to n asterisk. So what you will do, you need to find n asterisk and then go to the charts using n asterisk and lbx 2 times. One for n asterisk with lbx, one for n asterisk with lby. Okay, now another topic is quickly we go through it. We also don't go through it too far, or just for your information, not needed in the test or the the project. So this is the column under normal and moment. So the previous one we have n only, in this one we have normal and moment. So design of columns under axial forces and bending moment. Axial force N, bending moment M. So in this case, the column or the compression member are designed to resist N asterisk, design axial force, and M asterisk, design moment. So actually, this moment come from one of the cases that the moment come from is when you have a column under normal force. If the normal force acting exactly in the centroid or in the CG here, so we have only n. The moment will be 0. But in other cases, or in other like other buildings, we may have the column is under load, not eccentric, not concentric, sorry. So if the load is not in the centroid or is applied under eccentricity. So if the load is applied under eccentricity, then this frame or this column is equivalent to a column under a load in the middle and a moment. So the moment actually in some cases come from the eccentricity of the applied load. So if you applied a load similar to this example here, a load B equal to 1200, whatever the unit, with an eccentricity E. So this is equivalent to a load at the center with a moment applied. So N eccentric load is equivalent to N plus M. Okay, so this where the moment can come from. Another source of the moment and normal force together is members of frames, or let's say it columns of frames. So if we have columns of frame, so this column will be, or these columns are under normal force and bending moment. Okay, so this is an example of a portal frame. If we have a portal frame like that, so this is how the moment will look like. This is the bending moment diagram. We don't need to go through this. And also we will have an axial load diagram, something like this. The axial load diagram will be something like this as well. So if we look to one column, this column. So actually this column, if you cut anywhere in this column at the top here, so this column is under moment from here so this column is under moment here, M, and under normal force here, N. So this column of the frame is under M and under N. So when you design, you need to consider both together. So if we refer back to the design formula for design equation for columns, we just seen it earlier today. So we need to make sure that n asterisk less than phi nc. So we have n asterisk over n phi nc less than 1. So if it is less than 1, so this design is safe. So this if we have axial compression only. If we have bending moment only, so same formula for rafter, m asterisk should be less than phi mb. So we have m asterisk should be less than m asterisk over phi mb should be less than 1. If it less than 1, so this design is safe. So this is case of n only, normal force only. This case of m only. This just to understand the difference here. If we have n and m. So if we have n and m, we need to make a combination between the two cases here. So if we have this plus this will give us our combination. So in this design, we need to have n asterisk over phi nc for normal plus m asterisk over phi mb for moment, both of them together less than 1. If we satisfy this condition, so our column will be safe under n and m. So this is how the design of columns under normal force and bending moment works. So we need to satisfy this condition. Okay. In this case, we can use the beam column capacity tables or charts, but we will need to use the charts twice to design the column. So we need to go one time for axial load and one time for moment. To satisfy this formula. Okay, so as I mentioned, we will not go through this in detail. So you just need to focus on the first part, which is up to here. So we design only the column under axial loads, and then this again is a summary of what we have done today, and that's it for today lecture. So this is our last topic in the superstructure part. And next week in the classes, I will explain the example, the step-by-step design example for column. So after that, we will like conclude all the superstructure topics. And next week lecture of the superstructure, I will go through some of the instruction of the test and a quick revision about some of the final tests from last years, from previous years. Thank you. Do you have any question, guys, before you go? Thank you for attending today. Thank you, Syok. Thank you, Harrison. Thank you, Jazir. Thank you, James. See you next week and see you tomorrow in the class. Thank you.